Okay, Yonglong, you're up next. Try sharing. Okay, great.
Can you see my screen?
Yep.
And hear me well? Okay. I would like to begin by thanking the organizers for putting up such a nice program together and also giving me the opportunity to talk about our recent results. So I actually changed the title a little bit and decided to include some of the unpublished work that we have done. And I'm actually a new assistant professor in the department at Rice. But for all the work that I'm going to present, I actually done in Boston. It's a collaboration between the group of Amiya Kobe at Harvard and the group of Pablo Hale at the MIT, and we benefit a lot of theoretical support from the group of Ashwin Vishwanath. So for today's talk, I would like to basically tell you two things. The first thing is the observation of fractional Chern insulators in measuring angle twisted bilayer graphene. And then for the second part, I'll show you how we actually have gained some understanding about the interplay between the localized and the dispersive electron in measuring angle twisted trilayer graphene. And I think for this audience, I don't want to tell you how much the discovery of fractional quantum Hall effect have revolutionized our way of thinking. And then the very simple rule of thumb is if you can make integer quantum Hall effect and in the presence of Coulomb interaction, you can possibly see the fractional quantum Hall effect. And then this discovery has led to many new development, topological order, fractional charges, fractional statistics, and so on. And even although it was discovered 40 years ago, it's still quite an active research field. And only last year, we started to hear results about how to break these anyons. And also people have actually tried to couple these fractional quantum Hall state with superconductivity in order to create more exotic states. But as you all know, the emergence of fractional quantum Hall effect or quantum Hall effect itself relies on the application of a strong magnetic field. And actually, people starting from 10 years ago or possibly earlier, people actually have started to think about whether there's a way to get rid of this. So as I said, in order to get fractional quantum Hall effect, you start with 2DAC, and then magnetic field give you Landau level, and then in the presence of strong interaction, you get fractional quantum Hall effect. And the way to get an analog of fractional quantum Hall effect, that is the fractional Chern insulator, the starting point is actually quite simple. What you need is to find a material system get holes that's described by what's called a Chern band. And here you don't really need a magnetic field because the quantum geometric property of the electron, or namely the Berry curvature, is giving you that intrinsic magnetization. And then if you can manage to find this system, and then you can tune it to partial filling, and in the presence of strong interaction, you can, in principle, get fractional Chern insulator. And the motivation for looking for these states is because, in principle, they could emerge at a higher, or they could survive to higher temperature. And one big difference between Landau level, which is essentially a system with a Chern number of 1, for a generic Chern band, you can actually have Chern number 2, 3, 4, and then that means you can realize actually states that are beyond fractional quantum Hall, analog of fractional quantum Hall states. And then the fact that you can, in principle, stabilize them, down to zero magnetic field means that they are already very compatible with superconductivity. So I should mention that there is actually some realization of fractional Chern insulator, but it actually requires a very, very large magnetic field, even larger than what you would need in order to see fractional quantum Hall state. This is the work from Andrea Young's group at UCSB, where they look at Bernal bilayer aligned with HBN. And then in this case, the Chern band comes from the Hofstadter spectrum. And one of the limitations of this is that you in order to generate a Chern band, you actually need the magnetic field. Therefore, it's impossible fundamentally to use this strategy to realize a fractional Chern insulator in the zero field limit. So more recently, there's this very promising material platform. You heard a very nice introduction yesterday that's measuring twisted bilayer graphene, and then the band structure look like this. It has a pancake, and then there are a lot of exciting stuff seen and observed in this system. But what you need to know for this talk is that all these complicated band structure can be approximated by all the 4 copies of Dirac cone, 4 copies because you have spin and valley. And then this is protected by a composite symmetry called C2T. And if you can break, one of these symmetry or both of these symmetry, for example, if you align the sample with HPN, then the C2 symmetry would be explicitly broken. Then these 4 copies of Dirac cone would actually become isolated Chern bands, and they are all degenerate. And early experiment actually showed that this is indeed what's happening in the system. And one of the first experiments was done by looking at HBN aligned twisted bilayer graphene, and then they observed quantum anomalous Hall effect, filling factor 3. Basically, those bands you fill 3 out of 4. And the fact that you see quantum anomalous Hall effect means that you indeed have a Chern insulator. And later in the summer, there was a big wave of work from various groups showing that you actually can also achieve or stabilize Chern insulator without HBN alignment if you just apply a little bit of magnetic field. And the emergence of Chern insulator actually can happen at almost all filling, and it follows a pretty generic sequence. And all this is just to say that magical twisted bilayer graphene has almost the perfect ingredient for realizing fractional Chern insulator, because as I mentioned, you need Chern band plus a strong correlation, and then this is the case for twisted bilayer graphene. And that's what I'm going to tell you. This is the data we have obtained, and I will tell you in a minute how we detect this. But just to give you an overview, we actually detect a number of fractional Chern insulator and also other phases that are quite interesting. The technique that I use is called scanning single electron transistor. On the left-hand side, I'm just showing you how the tip look like. And then the way we do this is we pull a very small cross tip to form a very small tip apex of the order of 100 nanometer, and then make a quantum dot at the apex. And then I'm sure you're familiar with this. If you have a quantum dot, you will see Coulomb blockades. And then basically the current will oscillate as a function of external electrostatic potential. And what it means is that any small change in electrostatic potential will give you a large change in the current. Therefore, it's a very good electric field sensor. And then you can basically use some trick to use this to probe electron chemical potential and compressibility or inverse compressibility. And thereby, it's a very useful tool if you want to look for fragile incompressible states such as fractional quantum Hall and fractional Chern insulator. And the way it works is that imagine if you have a system that's described by that's gapped, and what you will see in the in our data is inverse compressibility as a function of carrier density, and then you will see a peak that corresponds precisely to the energy gap that you have on the left side. And what you need to remember is that often when you see a peak in d mu dn, it means that you have a gap state. And since this is not a very popular technique, I just want to say a few words about how people have used this in the past. People actually have used this to look at quantum phase transition. I'll talk a little bit about this towards the end. And one way to use this that's really nice is that you can use this to actually probe and measure the precise value of the charge carried by the elementary excitation in your many-body state. And if you are able to perform measurements as a function of magnetic field and temperature via Maxwell equation, you can also extract magnetization and entropy. And more recently, we have found a way to actually measure the chemical potential of charged neutral magnons in the quantum Hall regime. But for the purpose of the today's talk, what we need is actually a direct measurement of the local Chern number. And the most popular technique to do this is to measure the RXY. And if you see a quantized plateau, then you can basically extract the Chern number of the system. But another way to use this is to use what's called a strata formula. Basically, you monitor when the evolution of the gap as a function of magnetic field and density. And the really nice thing about the second method is that this can be done locally. And it was actually applied not 10 years ago to bilayer graphene, and at that time, even bilayer graphene cannot be made or prepared with very, very high quality. But nevertheless, using this method, these authors were able to detect a very fragile fractional quantum Hall state down to, I don't remember what denominator. And what we're going to do is to apply this technique to measure angle twisted bilayer graphene and then examine the slope of all these incompressible state that we see. So this is the data that I have already flashed at the beginning. So taken using the scanning SCT or measuring angle twisted bilayer graphene, you see that there are a lot of features, red features, and all these correspond to incompressible states. And the exercise that we're going to do is basically to extract the slope and the intercept of all these linear trajectory. And this is summarized in the lower panel. And then what you can do, or what we did, is to categorize all these incompressible states based on the value of the intercept and the slope. And if both of them are integer, then those are described by integer quantum Hall states, and so on and so forth. And then the highlight is that if you see something that has a fractional value, either a fractional intercept or fractional slope, it means that it's something unusual. And in particular, if the slope is fractional, it means that you have a fractional Chern, you observe a fractional Chern insulator. So what I'm going to do next is to go to part of the phase space where we have a pretty good handle on what's going on, and that is between filling factor 3 and 4, 2.5 and 4, and where the system is pretty well described by filling just one band, one of these Chern band in the system. And we can perform the same exercise and then trace out all these incompressible state that we see. And the fact that you find a fractional intercept actually immediately tell you that this state likely break translation symmetry, because that means that you're only filling every third of a unit cell in the Moire superlattice. But we can actually understand this the emergence of this state better. And this can be done by first examining the property of these Chern band that I introduced earlier. So this is the shape, the purple trace outline just a copy of this Chern band. And one important property associated with this Chern band is that since it's Chern band, it has barrier curvature. And in fact, the barrier curvature in this system is very concentrated near the center of the Riemann zone. And now if you want to break translation symmetry by, for example, doubling the unit cell, what you will do is basically to fold the band, cut this into half, and then shrink the Riemann zone. And what you will, the consequence of that is for those states that you fold back into the center, it will not feel any barrier curvature. As a result, the new band, the lower band, will basically inherit all the topological property of the initial band, whereas the upper band will have a Chern 0 number. Now you can go on and then try to look at basically work out the filling. And now if you want to try to, for example, explain the state we see at 7.5, what you can construct is take all these 4 bands or all these 8 band, because you double the unit cell, and then you can basically explain the emergence of this state by filling all the colored band, red and blue, and then while leaving the last gray band, there's a Chern 0 band ready, and then empty. And then if you sum up all the Chern number, then it all makes sense. And you can do the same for the states that have a denominator of third, and you can basically repeat the same exercise, and the trick is basically the same. Only the lower band will inherit will carry a Chern number because of the barrier curvature in this system is highly concentrated. And you can basically work this out, and then we find it's all consistent. And the most exciting part is when you increase the magnetic field further, and then this is shown in the upper panel, and then the traces the slope and the intercept are marked in the lower panel. What you see is that as soon as the magnetic field reaches 5 or 6 Tesla, all these vertical features that you saw in the previous slide, they actually disappear, and then instead they are replaced by all these slopey feature. But if you try to fit the slope, it's not quite an integer, and instead it takes the value of 2/3 and 1/3. And remember what I told you before, if you see a fractional slope, it means that you see a fractional Chern insulator. So what we found here is actually quite nice, because here these fractional Chern insulator, although they do not emerge at 0 magnetic field, they emerge at already 5 Tesla. That is significantly smaller than the 30 Tesla needed for the previous work. Now, if you try, you want to understand why we are getting all these numbers, you can actually go back to the sketch that I drew. We have 4 bands in total, and then since we see the very strong Chern plus 1 Chern insulator from filling factor 3, what it means is that the system probably already filled 2 red band and then 2 one blue band to make a total Chern number of 1 plus 1, and leaving 1 Chern minus 1 band empty. And then if you assume that when you fill 1/3 of this band, it makes a state that's analog of a 1/3 Lafland state, thereby contributing a 1/3 of slope, then or minus 1/3 of slope, because the band carry a Chern number of -1, then you can actually make sense of all these numbers, and similarly you can do the same exercise for the other state. So this is quite nice, but one thing that troubles us is, why don't we see a fractional Chern insulator at 0 magnetic field? And you probably have already noticed that the way I drew all these sketch is quite different. The top one, I have this only the bottom section of the sketch is colored, whereas for the FCI, the whole band is colored. What it means is that actually the emergence of CDW or versus fractional Chern insulator, they place completely opposite requirement on the Berry curvature distribution in the system. For fractional Chern insulator, you actually want the Berry curvature to be well spread out, very much like in the case of Landau level. And you can actually do more careful calculation and examine or quantify how much the Berry curvature is fluctuating in the momentum space as a function of some tunneling parameter in the system. And what you will find is that indeed there is a part of phase space where fractional Chern insulator is favored, because the Berry curvature distribution is more homogeneous, and the rest of it would favor charge density wave. And you can extend this kind of calculation to basically finite magnetic field. And what our collaborator found is that actually when you apply magnetic field, the Berry curvature distribution become more and more homogeneous, and then at some point it below a certain threshold where fractional Chern insulator would become favored. And you can basically do this calculation over a larger phase space as a function of this tunneling parameter and also magnetic field. And what we find is that around roughly 1.15% of a flux quanta, that's around 5 Tesla, you would start to favor a fractional Chern insulator. And then we conclude that the main role of the magnetic field is to flatten the Berry curvature. And we have also looked at other region of the filling factor and also magnetic field, and observe a number of other fractional Chern insulator that are marked by all these red lines. And some of them we can explain them the same way as what I described to you. Some of them will require us to invoke some symmetry, the fractional Chern insulator to live on a symmetry breaking charge background. And some of them we can't really make sense of it. And then what we can say at the moment is that they are there. So this brings me to the summary of part 1. So we saw a number of fractional Chern insulating states imagining electricity bilayer graphene, and then I think some of the interesting future direction would be try to probe what's the charge carried by all these weird fractional Chern insulating state that we saw. And of course, one of the pressing questions is to see whether we can find any strategy for stabilizing fractional Chern insulator down to 0 magnetic field. And one way to do that is maybe to explore other material system, and that's precisely the motivation for which we have started to look at magic angle twisted trilayer graphene. So magic angle twisted trilayer graphene is quite similar to magic angle twisted bilayer, and basically you have 3-layer graphene. You have basically A twist A, and the really nice thing about this system is that the band structure or the electronic property of trilayer can be understood as the sum of twisted bilayer graphene plus a monolayer graphene. And the only changes is that the twist or the magic angle changes because of the geometric condition. And instead of 1.1 degree, now 1.56 degree is the magic angle for trilayer. And then now if you convert this number to the Marelli length scale, you get 9 nanometer instead of 13 or 14 nanometer for the bilayer, which actually motivated us also to look at this system because it probably means that the Coulomb interaction could be stronger in this case. So if you go to a full calculation for the band structure, what you will get is indeed these flat bands, the mark in orange yellow, and then these purple dispersive massless band that pretty much behave as the monolayer Dirac cone. And then if you do not break the inversion symmetry, which means that if you do not in practice apply a displacement field, then these two bands would not talk to each other. Now, if you think about applying a magnetic field to this system, what it will do is basically for this massless part of the band structure, it will very quickly quantize into Landau level, and then because it's a direct system, very quickly in practice around 0.5 or 1 Tesla, you will all these Dirac cone will become Landau level, and then lefting over 1 angle 0 Landau level, and then for the flat band part, it will just do complicated thing that I mark in red, and that's basically the simplified version of the half-sided spectrum of the flat band. And another motivation for looking at this trilayer graphene system is because this dispersive band, this purple band that I drew previously, is important for superconductivity. As suggested by a more recent work where people have fabricated not only trilayer but also quadruple layer, pentable layer. One of the common feature is that you will always have flat bands, but in addition you will have all these dispersive bands as shown in all this band structure calculation. And then the surprising thing is that superconductivity is ubiquitous in all this system, and you can perhaps even argue that once you go to more layer, or the other way to put it, if you want, is introducing more dispersive band, you can actually extend the phase space where you can stabilize superconductivity. So this was the second motivation for us to look for to basically understand what is the role of dispersive bands in all this twisted multi-layer system. And then we chose trilayer graphene because the band structure is much simpler. And so the device we look at, it's just a standard magic angle trilayer graphene. The only difference is single gated because we do scanning probe. And then we have characterized this device using transport, and then we do see robust superconductivity on both electron side and hole side. Though some of the TC is not super high, it's around 1 Kelvin, or for the electron dope side, and then the hole though is maybe 2-3 Kelvin. So we took this device and then look at it under scanning SCT, and then basically perform the same measurement, inverse compressibility as a function of filling factor and magnetic field. And we can do the same exercise basically to trace out what are the slope and the intercept that we see in this data set. And what we find is that there are basically there are a number of incompressible states at near integer filling that persist all the way down to to zero magnetic field, and then I'll talk about that later. Unfortunately, we do not see any signature of fractional Chern insulator in this system, which probably means that there are something that we still understand as what's required for stabilizing FCI. But nevertheless, this data actually can inform us on the band structure of the system. And what I mean by that is, if you go back, to this simple sketch that I drew, you have basically the Dirac cone that quickly get quantized into Landau level and then leaving behind the n equals 0 Landau level. And then if this will actually allows you to do the head count of the Chern number. What I mean by that is that if you look at the states on the electron side, you will the n equals 0 Dirac cone, n equals 0 Landau level from the Dirac cone actually contribute to a Chern number of +1. And then if you look at the whole dope side, it actually contributes to a Chern number of +2 and then -2. And then you can basically do all these math and break down and then understand that pretty well. Matt, how much time do I have?
You can finish. I mean, we're supposed to leave 5 minutes for questions, but I mean, the hard cutoff is in about 5-ish minutes. Okay,
I'll go a bit faster then. So all this is just to say that from the Landau fan, the system is well described by Dirac cone plus the flat band with the twisted bilayer, and then we can also extract the spectrum and then really visualize this Landau level in this from the Dirac cone, and then it's all very consistent. And I just want to maybe talk about this incompressible state near zero magnetic field. That seems quite weird because previous transport experiments do not see them at zero displacement field. And then it also exhibits these weird glitches. That if you try to follow the linear trajectory, there's an offset, and actually that marks the magnetic field at which you start to send out the Landau level from the Dirac cone. But what I find really interesting is that it probably means that wherever you have for example, right here you have this incompressible state, the offset probably correspond to how much monolayer electron that you have at zero magnetic field. And of course, the one of the questions that puzzle us is what is the nature of this incompressible state? And then there are two popular candidates. One is the whole system is gapped, and the other candidate is the system just exhibit low density of state. And then the way to look at this is very useful way to look at this is what's called a localized state. It's been applied in the past in quantum Hall and fractional quantum Hall. Basically, the short introduction to this is that if you really have a true incompressible state, then you will see all these spikes because the density modulation in your system will basically unavoidably form this quantum dot, and then you will the screening will fail if the neighboring region become incompressible, and then you will see these peaks. And then we did that for all this incompressible state that we saw. And what we found is that at the higher field portion, we see these nice glitches. However, they disappear for the lower field, which probably means that at low magnetic field, we don't really have a truly gap state. But instead, in the TBG sector, we have a correlated insulator, whereas in the Dirac sector, we actually fill up some electron up to some level. And then you can actually use this to quantify how much electron from the Dirac sector we have, and then we find this what we call the residue derived electron at integer filling. And then remember, for example, near Yonglong 2, as you dope a little bit more electron, you start to act superconductivity. And then I think that it would be interesting to think about what's the implication of superconductivity. And the last thing I want to talk about is we actually also see quite some unusual feature near the charge neutrality, namely the negative compressibility, and that's basically all these dark blue feature. And then one thing that you can already tell from this is that we observed all the singly degenerate quantum Hall states all integer filling. And then the largest slope that we see is ±6, which means that everything is happening within the n equals 0 Landau level between the dispersive and the flat band, and then the head count works pretty well. And because everything happened within the n equals 0 Landau level, we can actually replot this as a function of a Landau level filling, and then you start to maybe get a better handle on what's going on. All these negative compressibility region basically interrupt the incompressible state and integer filling. But the weird thing is it extends over a large density range. And this actually has been seen in the past in the context of fractional quantum Hall effect. And the reason why this happened is because in the fractional quantum Hall regime, you have all these compersive fermion and Landau level, and then you have actually a lot of degeneracy or possibility for filling, choosing, which level to fill. And all these interruption correspond to spin and or Vallée phase transition between all these composite fermion level. And then at the magnetic field at which this crosses or where the incompressible state get interrupted is governed by the energy separation between this level and also the Zeeman effect. And what we can do is basically to construct a very similar phenomenological model. And then here, the key ingredient is that there's energy offset between the Dirac band, the Dirac point of the Dirac band and the Dirac point of the flat band. And as predicted by the single particle band structure calculation. And then you can already go and then see that, for example, for nu equals -5, you have two options. You can either fill the Landau level from the Dirac sector, or you can fill the Landau level from the flat band sector. And we can go and then try to make a more a little bit more complicated calculation, and then you see that that's shown in the bottom panel. And the lesson we learn is that all these negative compressibility actually marks the boundary where you start to depopulate the Landau level from the Dirac sector, populate, sorry. So I know I'm running out of time. I'll skip the summary. I think I'll just take the opportunity to make an advertisement. We are now hiring. I'm gonna establish a new group at Rice, and then if you are interested in learning and exploring how this scanning single electron technique can be used, and also other kind of scanning modality, please feel free to reach out to me. And let me just show the acknowledgement again, and sorry for running over time.
Okay, thanks, Yonglong. We have time for a quick question. Okay, Saeed, you were first.
Yes, thank you for the talk. My question is that, is this experiment also done with the finite displacement field?
So as I mentioned, the device geometry that we have used is actually singly gated. And then the other side is basically open boundary condition. And then in principle, there's some effect of finite displacement field, although it's very small. But based on the data that we have seen, the Landau fan data that we have seen, it's actually very well described by this simple picture where the Dirac cone and the flat band are hybridized. So
yes.
I would argue that the system is well described by decoupled in the single particle sense, decoupled flat band and Dirac band, and that's also maybe why we are seeing this.
Yeah, the reason I was asking is that maybe if it's possible with displacement field to gap out the Dirac cone, then
with displacement field, yes, it's possible to gap out, and actually there are some more recent transport experiments have shown insulating behavior near nu equals 2 in the presence of the finite displacement field. And I want to emphasize that we see incompressible behavior at all integer filling, but what we found using this localized state spectroscopy technique is that at low magnetic field, the system is only partially gapped. And it's more like a semi-metallic or metallic system, because you actually feel the monolayer Dirac cone up to pretty high in Fermi energy.
Okay, so we can do one more quick question, but then we really got to move on. So Tarun, you were next.
Thanks. So in the first part of your talk, is the transition between the fractional Chern insulators, any of them, and the CDW, was it is it a second order transition? And if yes, can you extract some critical exponents?
That's a very good question, but I should say that here it's not quite. I will refrain from calling this a phase transition, because as you can see here, they actually, I mean, they meet, but they actually emerge as slightly different carrier density or filling factor. For example, here, you know, it's 3.5, and then it's not like it directly transition. It's more like, I would rather call it a CDW dominated regime and then FCI dominated regime.
I see.
It's not really like there's a phase space where, you know, you have a phase separation or things like that.
Okay. I mean, I was looking at your paper. I mean, just the figure, for example, in the flux and the W0 over W1 plane, the two-dimensional plane, there's a, at least it seems like there's a transition in that phase in this 2-parameter phase diagram with flux and the ratio of the hoppings. But anyway, but
yeah, that's true. But this is not a continuously tunable parameter. For this one, yes. For magnetic field, yes.
But you won't. But with this magnetic field, you will still not call it a. I mean.
Yeah, but well, it's true that you enter a favorable regime for FCI, but you know, because when you apply magnetic field, you also need to account for the Strader formula. Basically, you need to attach more electrons.
Yeah, no, I understand. Flux. This is not the way to discuss transition. I agree. Thanks.
Okay, guys, I think we got to move on. So thank you very much.